Have you ever stopped to think about what really happens when you click a button? I mean, really think about it. That one simple action kicks off this incredible, secret chain reaction deep inside your computer. In this explainer, we're going to use that single click as our key to unlock the door and understand how computers actually think, all the way from the basic building blocks of code to this invisible dance that's happening inside their memory.
So, how do you even get a computer to understand the real world? Well, it all boils down to this really simple but incredibly powerful idea. At its core, every single computer program separates what something has from what it does. Let's just think about a dog, right? What does a dog have? Well, it has a color, a breed, a name. That's its data, its properties. And what does a dog do? It barks, it runs, it wags its tail. Those are its actions, its behaviors. You know, this fundamental split between what something is and what it does is pretty much the organizing principle for almost all modern software.
Okay, so let's zoom in on that does part, the actions. In the world of programming, an action has a special name. It's called a method. And what's wild is that every single method, whether it's adding two numbers or, launching a rocket, shares the exact same basic anatomy.
First things first, every action has to have a label. It's just a simple descriptive name like calculate, send, or add that tells the computer, and just as importantly other programmers, exactly what this piece of code is supposed to do.
But, an action usually needs something to act on, right? If I just walk up to you and say, add, you're going to look at me and say, add what? That what is the input. A method needs some data to work with, like the two numbers it's supposed to add before it can do its job.
And then you've got the engine room. This is the how. It's the step-by-step logic, the actual work being done. For our add method, this is the part of the code where the computer actually performs the addition. It's the brains of the operation.
And finally, after all the work is done, a method usually has to hand something back. I mean, if you ask it to add 5 and 5, you expect to get 10 back, right? That result, that answer, is the output. It's the whole reason you asked it to do the action in the first place. Okay, let's put it all together and get the official lingo down. What we were calling the input, programmers call parameters. That core activity, the engine room, that's the body. And the output, the result it hands back, is known as the return type. So you've got name, parameters, body, and return type. That's it. You now understand the fundamental DNA of literally every single action a computer can take.
Now, this is where it gets really interesting. Seeing this stuff in action inside the computer's brain, well, it's not a brain, it's memory. When we ask the computer to run one of these methods, this really fascinating dance starts to happen.
So our memory story has two main characters. First up, you have the stack. Think of the stack as this super organized, neat and tidy space for keeping track of what tasks are running right now. Then you have the heap, which is kind of like a big open warehouse where all of our data and objects are stored.
The second our program kicks off, the main task gets its own little workspace created on the stack. This is called a stack frame. You can think of it like the very first item on the computer's to-do list. It's ground zero.
Okay, next up, let's say our program creates a calculator object. It has to live somewhere, so it finds a nice spot in that big open heap. And for now, it just sits there, waiting for instructions.
Now watch this. This is the magic moment. The second we call our add method, bam, a brand new frame for add gets placed right on top of the main frame. This is how the computer prioritizes. It means, okay, pause whatever you were doing in main and focus 100% on this new add task. Whatever is at the very top of the stack is the only thing the computer is thinking about at that exact moment.
And what happens as soon as the add method is finished doing its calculation? Poof! Its stack frame is instantly destroyed. It's popped right off the top of the stack. This is the golden rule of the stack. Last in, first out. The computer now sees the main frame on top again, and it just picks up right where it left off, like it never missed a beat.
So this leads to a really important question. What happens to our calculator object? It's still sitting over there in the heap, but when the program ends, even the main frame is gone. Now, absolutely nothing in our program is pointing to it anymore. It's become an orphan, just
abandoned data. And programmers have a great name for this. It's called a garbage object.
Okay, so you can imagine that this mess of abandoned objects could get out of hand pretty quickly. And this leads us to one of the most powerful, time-saving features in modern programming languages like Java, the ability to automatically clean up its own mess.
Get this. Believe it or not, roughly every 2 milliseconds, this automatic process called the garbage collector does a full sweep of the heap. It's like a little Roomba for memory. It's constantly looking for any of those garbage objects, any data that's been abandoned. And when it finds one, it reclaims that memory, making it free to use for new objects.
So why does this matter so much? Well, it's a total game changer. This automatic cleanup prevents all sorts of nasty bugs, like memory leaks, it makes programs way more stable, and, this is the big one, it frees up developers to actually focus on building cool features, not meticulously managing every single byte of memory by hand.
All right, so computers are smart enough to take out their own trash. That's a pretty fundamental detail about how they work. But how does knowing this low-level stuff really matter in a world where AI can just write code for us? Let's connect the dots.
You know, the reality is, AI isn't really replacing developers. It's changing the job. It's creating this huge demand for a new kind of developer, someone who knows how to use AI as an incredibly powerful tool. I mean, just look at how AI shortens the time it takes to go from just an idea to a real working product. A feature that might have taken 4 months before could now be done in 1. That doesn't mean fewer jobs. It means companies can now build more stuff faster, which actually increases the need for skilled people who can guide that whole supercharged process. And this is the key takeaway of this whole thing. Knowing what's happening under the hood, understanding why a certain piece of code that an AI spit out might create thousands of those garbage objects and slow your whole app to a crawl, that knowledge is what separates the architect from the bricklayer. See, anyone can tell an AI to lay bricks, but only someone with that fundamental knowledge can actually design the building, make sure it's stable, and build something truly new and innovative.
So the real question isn't, will AI replace me? The real question you should be asking is, will I be replaced by a person who knows how to use AI effectively? Understanding these fundamentals, the stuff we just talked about, that's how you become that person. The foundation is everything. So, are you ready to build yours?